Hi, my name is Sohaib, and this thesis investigates the flexural behavior of concrete beams with high-strength steel. My advisors are Professor Michael Bartlett and Professor Magid Youssef. So currently the CSA standard 823.3 limits the maximum yield stress of steel reinforcements to 500 MPa, and high-strength reinforcements have yield stresses which exceed 500 MPa. So the current standards for conventional steel grades haven't been fully investigated for beams which are reinforced with high-strength steel. So the overall objective is to therefore examine the current provisions in 823.3 for the design of beams with high-strength steel and check their adequacy. Chapter 2 investigates the impact of high-strength steel on curvature ductility ratios. Chapter 3 calculates the maximum permissible moment redistribution in continuous beams, considering ultimate limit states and serviceability limit states. And Chapter 4 investigates the adequacy of deflection provisions in 823.3. So Chapter 2 is the flexural ductility of concrete beams reinforced with high-strength steel. The primary objective of this chapter is to calculate the curvature ductility ratios for both the conventional and high-strength steels. Another objective is to develop means to quantify the steel stresses at ultimate limit state and to check the flexural balance failure criterion in 823.3 in beams reinforced with high-strength steel. This table is showing the mean mechanical steel reinforcement properties for the different steel grades that were investigated in this chapter, which include A23.3 grade 60 and 100, A706 grade 60 and 80, and A1035 grade 100. F sub y is the mean yield stress of the steel reinforcement. Epsilon sub sh is the strain at the onset of strain hardening. E sub sh is the Young's modulus at the onset of strain hardening. Epsilon sub u is the ultimate steel strain. F sub u is the ultimate steel stress. And epsilon sub f is the fracturing strain in the reinforcement bar. This data is from Mander and Matamoros. This figure is showing the stress-strain relationship for different steel reinforcements. On the vertical axis we have the steel stresses, and on the horizontal axis we have the steel strains. Looking at this figure, if we look at A706 grade 60, it's showing the highest ductility among the steel grades. And high-strength reinforcements, which are A1035 grade 100 and A615 grade 100, have one of the smallest ductilities. And apart from A1035 grade 100 steel, all the other steel types are showing a distinct yield point, whereas A1035 has a roundhouse curve around the yielding region. The first step in calculating the curvature ductility ratio is to come up with the moment curvature relationship, and this is the cross-section that was used. According to 823.3, the yielding curvature can be determined from the strain diagrams when the steel is yielding, and yield is defined when the steel stress reaches the steel yield stress, and the ultimate curvature can be calculated from the strain diagram at ultimate, and ultimate is defined when the extreme fiber concrete compressive strain reaches its maximum value. Curvature ductility is the ratio of the ultimate curvature to the yielding curvature. So this figure is showing the concrete compressive stress variation on the vertical axis for the different idealizations, which include Carrera, Thornfield, and Wheat. And on the horizontal axis, we have the steel strain. The initial ascending branches of all the idealizations are very close and are approximately linear up until the peak concrete compressive stress. The vertical arrows are showing the strains which correspond to the peak compressive stress, and the increase as the peak compressive stress increases. After the peak compressive stress is achieved, then the descending branches are diverging, and the difference between the idealizations as they diverge increases as the peak concrete compressive stress increases. In the moment curvature analysis of this chapter, The idealization by Carrera and Chu was used because it's simple to implement and it gives good results when compared to other idealizations. Figure on the right is showing the variation in steel stresses on the vertical axis with the strains in the horizontal axis. The graphs labeled equations 2.16 and 2.17 are for referring to the steel idealization by Mander and Matamoros, which was the idealization that used in the moment curvature analysis of this chapter, and in this figure is being compared to the other results by Yosefani for A615 grade 100 and Mast for A1035 grade 100, and the results are very close, which is good. So to implement the concrete idealization by Carrera and Chu, we have to go with the layered approach, in which the neutral axis depth, which is labeled C, is divided into 30 layers from 1 to 30, and the thickness of each layer is C divided by 30, and because the strain is assumed to be linear, as shown in the strain diagram, the concrete strain on top of each layer can be calculated, which is labeled epsilon sub Ci. Once we have the strain, we can determine the stresses, which is labeled sigma sub Ci. And once we have the stresses on top of each layer, we can calculate the average stress in each layer. And once we have the average stress, we can calculate the force in each layer, which is labeled C sub Ci. And we can sum all the forces and we can get the concrete compressive force in the whole compression region. And we can determine the distance from the extreme fiber to the compressive force in each region, and we can determine the moment due to the compressive force in each region. If we sum all the moments up, we get the total moment due to the concrete compression. So to conduct the moment curvature analysis, we first have to select an extreme fiber concrete compressive strain and also choose a neutral axis depth. From there, we can calculate the strains in the steel and the concrete, also the stresses and the forces, so the concrete compressive force and steel tensile force, and we have to equal those to 0 because we have to maintain a static horizontal equilibrium. If the forces are in 0 and if the concrete compressive force is smaller than the steel tensile force, then we have to increase the neutral axis depth. But if the concrete compressive force is greater than the steel tensile force, then we reduce the neutral axis depth, and we keep doing this until our forces are equal to 0 when we sum them up. Then we have to compute the moments, and if we find that the moment in the current iteration is smaller than what we had in the previous iteration, then we have to stop the analysis because we've reached the ultimate moment. Otherwise, we have to keep increasing the extreme fiber concrete compressive strain, and we keep doing this until we reach the ultimate moment. So once we got our results for the moment curvature relationship, we can determine the load deflection results from the moment area theorem. And once we had those, we compared them to the Yosefani experimental results in beams reinforced with A615 grade 60 and A615 grade 100. In the experimental results, the top cover spalled, which reduced the ultimate moment capacity. So basically, the ultimate moment capacity was reached at a smaller extreme fiber concrete compressive strain, which you can see here. Previously, I mentioned that A1035 grade 100 steel doesn't show a distinct yielding point, and when determining the moment curvature relationship in beams reinforced with A1035 grade 100 steel, I use the equal area method, which basically encloses the areas under the actual and the bilinear curve and generates an equivalent yielding point. For the other steel types, such as A615 and A706, which have a distinct yielding point, I didn't have to use the equal area method. So this figure is showing the variation in the curvature ductility ratios on the vertical axis with mechanical reinforcement ratio on the horizontal axis. And just looking at this figure, we can conclude that curvature ductility is approximately inversely proportional to mechanical reinforcement ratio. And for a mechanical reinforcement ratio of 0.15, we get the largest curvature ductility ratio in A706 grade 60. And for high strength reinforcements, which include A1035 grade 100 and A615 grade 100, they're showing us the smallest curvature ductility ratio. And when finding the curvature ductility ratios in this figure from the moment curvature relationship, it was assumed that the extreme fiber concrete compressive strain was limited to a value of 0.0035, which in the second figure here was removed. And if we take a look at mechanical reinforcement ratio of 0.15 again, A706 grade 60 still has the highest curvature ductility ratio, but it's slightly increased, and A615 grade 100 and A1035 grade 100 still have the smallest curvature ductility ratios. So a regression analysis was performed on using the data from the previous figures, and a model was fitted into determining the line of best fit. So this is the model shown where beta sub 0 is the estimate for A615 grade 60 steel, beta sub 1 is for A706 grade 60, beta sub 2 for A706 grade 80, beta sub 3 for A615 grade 100, and beta sub 4 is the estimate for A1035 grade 100. I sub 1 to I sub 4 are the indicator variables for the different seal grades, and epsilon is the error term. And basically, in conclusion, when we constrained the extreme fiber concrete compressive strain in our moment curvature analysis, then all the parameters were statistically significant. But if we didn't constrain the extreme fiber concrete compressive strain, then they were all statistically significant except A615 grade 60 and A706 grade 80. This is a figure which shows the steel stress at ultimate plotted on the vertical axis and mechanical reinforcement ratio on the horizontal axis. The open marker are instances where the maximum moment was achieved at a extreme fiber concrete compressive strain which was smaller than 0.0035. And regression analysis again was performed, and fitted equations, as you can see in the table, were generated. And these can be useful for a designer, especially for a beam reinforced with A1035 grade 100 steel, because this steel doesn't have a distinct yielding point. So for a given moment demand, they could calculate the mechanical reinforcement ratio, and once they had that, they could use one of the equations and determine the steel stresses at ultimate. Balanced flexural failure was also checked in beams reinforced with the different steel types, and balanced failure in the analysis was defined as the extreme fiber concrete compressive strain reaching a value of 0.0035 and at the same time the steel yielding. And the nominal yield stresses as well as the mean yield stresses were used in the moment curvature analysis, and once the balance failure was achieved, the neutral axis depth, which is labeled C, was recorded, and it was compared with the A23.3 results, the 19th edition of A23.3, which is shown in the equation on the bottom left, where D is the depth of the beam cross section. And basically, the 19th edition of A23.3 was satisfactory because it was conservative when compared to the moment curvature relationships. So in conclusion, the curvature ductility ratio is approximately inversely proportional to the mechanical reinforcement ratio. A706 grade 60 has the greatest curvature ductility ratio, High strength reinforcements, which include a 615 grade 100 and a 1035 grade 100, have the smallest curvature ductility ratios. The fitted equations for steel stress at ultimate can be used to determine the steel stresses if we have a moment demand, which is especially useful in beams reinforced with a 1035 grade 100 steel. And the 823.3 balance conditions were satisfactory as they were checked with beams reinforced with the mean yield stress and the nominal yield stress in the moment curvature analysis. Chapter 3 is the moment redistribution limits for beams with high strength steel. So moment redistribution occurs in ductile, statically indeterminate structural systems. And if we have a continuous beam and we apply a uniformly distributed load on all the spans as shown in the figure on the left hand side, then we get critical positive and negative linear elastic bending moments as shown in the figure on the right hand side. And assuming that one of the critical section reaches its yielding capacity, then additional moment that's being applied at that critical section is going to be redistributed to other less severely critically loaded sections, as shown again in the figure on the right hand side, until all the sections yield basically and sufficient number of plastic hinges form on the beam, which makes the beam unstable. So the full extent of moment redistribution took place. So the figure on the left is going to show a case of complete collapse mechanism in two span beams that's continuous over the interior support. The figure on the right is showing the moment curvature relationship. Moment is plotted on the vertical axis and curvature is on the horizontal axis. Under this applied loading, which is labeled W, the first plastic hinge is going to develop at the support section, and under this loading, the span section still hasn't yielded, so the point A in the span section is still in the linear elastic phase. But if we increase the load on this beam, then the additional moment that's being applied at the interior support plastic hinge is going to be redistributed to the span section until the span also yields, and that's point B in the span moment curvature relationship. And if we keep increasing the load on the beam, then point C is reached at the interior support, and that's when the beam would fail. Now, if the inelastic rotational capacity of the first plastic hinge that forms in a continuous beam is limited, then we may get an incomplete collapse mechanism. So taking the same beam example as before and applying a uniformly distributed load W on it, the first plastic hinge is going to develop at the interior support section, and that's point A at the interior support. And under this same loading, the span section still hasn't yielded, so point A on the span section is still in the linear elastic phase. If we increase the applied load on this beam, then the interior support section plastic hinge is going to reach its ultimate capacity because it didn't have enough inelastic rotational capacity for a second hinge to form, and that's why the point B in the mid-span section still hasn't yielded. So the inelastic rotational capacity of a plastic hinge is proportional to the flexural curvature ductility ratio, and clause 9.2.4 of 823.3 limits the maximum redistribution of negative moments in continuous beam to the lesser of 30 minus 50 C over D, where C is the neutral axis depth and D is the depth of the beam cross section, or the lesser of 20%. Beams which are reinforced with high strength steel possess a lower curvature ductility ratio for a given mechanical reinforcement ratio, and because of this, they also have a smaller inelastic rotational capacity. And moment redistribution can reduce the seal area in a beam cross section, and if we consider high strength reinforcements, then they also reduce the seal area in beam cross sections, which basically can increase the steel stresses at serviceability limit state, and they can exceed the 0.6 Fy approximation that we use, and it may lead to unserviceable crack widths. So overall, the total objectives are basically, are the limits in clause 9.2.4 appropriate for beams reinforced with high strength steel, and will the combination of moment redistribution and high strength reinforcement lead to unacceptable crack widths? So first, I'd like to talk about the procedure on how I determine moment redistribution, then go over the sensitivity analysis, which includes the steel type and steel quantity, as well as the concrete compressive strengths that I'm using in the analysis. Check the adequacy of clause 9.2.4 and whether it can apply to beams reinforced with high strength steel, and review the total moment redistribution at ultimate limit states given the serviceability limit state constraints. So to conduct the parametric study of moment redistribution in two-span beams, we have to start with the interior support reinforcement ratio selection. And when we're determining the moment at the interior support, we have to assume that the live load is being applied on both spans. Then once we're finding the span section reinforcement ratio, we're assuming that the live load is applied on one span because that's a critical case when designing the span section in a two-span beam. Once you've designed the critical positive and negative moment sections, we can find the moment curvature relationship for both of those sections and fit a bilinear approximation. Once we have that, we can use the yielding and the ultimate points from the moment curvature relationship to define the plastic hinges in SAP 2000. In SAP, we also have to define the live and dead load combinations, and we have to define the nonlinear analysis options, which include how many load steps we want, and we have to divide the total applied and dead load combinations into smaller load increments. And after we run the analysis, we can access the moment rotation results at a specific load step, and we're checking to see if the first plastic hinge in our continuous beam has developed, and as long as it hasn't, we have to keep increasing the load on the beam until we get the first plastic hinge. And once we get it, we have to record the yield moment, or the moment that was needed for that first plastic hinge to develop. Again, we have to check if the second hinge has developed in our two-span continuous beam, and as long as it hasn't, we keep increasing the load. Once we get the second hinge to form, we know that we've achieved collapse load, and we can determine the linear elastic collapse moment, which is M sub C. Then from there we can find the total moment redistribution using the bottom right equation. So the variables that were investigated were concrete compressive stresses of 30 and 70 MPa, steel types A615 grade 100 and A706 grade 60, and these were selected because A615 grade 100 has the smallest curvature ductility, A706 grade 60 has the largest curvature ductility, and also we're applying live loads on one span and on both spans. So this figure is showing the results. On the vertical axis, we have the total moment redistribution in beams reinforced with A615 grade 100 and A706 grade 60 steel, and it has a concrete compressive stress of 70 MPa. On the horizontal axis, we have mechanical reinforcement ratio. If we're applying our live load on one of the two spans, then regardless of what the reinforcement type is, we are seeing a case of complete collapse mechanism, because the first plastic hinge is forming at the midspan section, and because the midspan section has a smaller reinforcement ratio, it has a larger curvature ductility ratio, and therefore a larger inelastic rotational capacity, so it allows for a second hinge to develop at the interior support section. When we're looking at live load being applied on both spans, and up until a mechanical reinforcement ratio of 0.2, we're seeing complete collapse mechanism cases, and that's where sufficient number of plastic hinges are developing. But as the reinforcement ratio increases, the inelastic rotational capacity is decreasing, and therefore we start seeing incomplete collapse mechanism cases towards the higher mechanical reinforcement ratios. If we look at the total moment redistribution results for concrete compressive strengths of 30 MPa and for 70 MPa, which is the figure on the right hand side. And let's first consider the complete collapse mechanism cases, which are the values to the left of the vertical dashed line. To the right we have incomplete collapse mechanism cases. And as long as a complete collapse mechanism is forming, then regardless of the concrete compressive strength, we are seeing a total moment redistribution of about 10%. So we can conclude that as long as a complete collapse mechanism forms, then concrete compressive strength is not that significant. If we compare our results to the 823.3 limit, we can see that the 823.3 limit is conservative. This figure is showing the variation in maximum moment redistribution on the vertical axis with the reinforcement ratio on the horizontal axis. The two graphs given are the 823.3 limit in beams reinforced with a 706 grade 60 and also the 823.3 moment redistribution limit in beams reinforced with A615 grade 100. And these are both for the maximum moment redistribution at ultimate limit state. If we add in the maximum permissible moment redistribution in beams, which satisfies the ACI 318 criteria, and beams reinforced with A706 grade 60 and A615 grade 100 steel with reinforcement bar spacing up to 50 millimeters, then the 823.3 limit is not conservative because it's allowing a total moment redistribution at ultimate limit state to exceed the serviceability limit state, so serviceability isn't being satisfied. But if we reduce the reinforcement bar spacing from 250 millimeters to 100 millimeters, then the 823.3 limit is conservative. So it actually depends on multiple factors whether our serviceability crack width criteria is going to be satisfied. And here I'm using the ACI 318 crack width criteria. So therefore, if a full plastic collapse mechanism forms and the moment redistribution is independent of the steel grade and the quantity of reinforcement, if a full plastic mechanism doesn't form, then a beam reinforced with A615 grade 100 steel will exhibit less moment redistribution than a beam which is reinforced with a 706 grade 60 steel with the same mechanical reinforcement ratio. The current provisions in clause 9.2.4 are conservative, and it's recommended that the crack width at serviceability be checked at all sections when the moment redistribution has been used to reduce the steel area that's required at ultimate limit state. The steel stress at serviceability should be computed using the crack moment of inertia instead of assuming the serviceability stress approximation of 0.6 Fy. Chapter 4 is deflection in concrete beams reinforced with high-strength steel. So basically, when we use high-strength reinforcement in beam cross-sections, we can reduce the seal area. But a reduced seal area also reduces the crack moment of inertia, which can reduce the flexural rigidity of the beam, and it can lead to unserviceable deflections. Table 9.2 of 823.3 gives the minimum beam height, and which is labeled 8 sub min, and beams which exceed this minimum beam height are considered to have serviceable deflections. This is showing table 9.2, and for the different beam types we have the different minimum beam height factors, where L sub n is a clear span length, and in this chapter it's going to be taken as 5 meters. So the objective is to check if high strength reinforced beams that have minimum beam heights satisfy the long-term incremental deflection limits, and also investigate whether the minimum beam height correction factor S sub f can be relaxed, where S sub f increases as the yield stresses of the reinforcement bars increase. So a beam which is reinforced with high strength steel is going to have higher minimum beam heights due to this correction factor. This figure is showing the variation in deflections on the vertical axis and the time in days in the horizontal axis. In this chapter, Gilbert's method was used to calculate all the different types of deflections, which include the shrinkage deflection labeled delta sub sh, which is due to the horizontal deformation differences in the compression and the tension region of a beam cross-section. We also have the instantaneous and creep deflections due to own weight, which is labeled delta OW. We have creep and instantaneous deflections due to superimposed dead load, labeled delta SDL. We have sustained live load, creep, and instantaneous deflections, labeled delta SLL. And we have instantaneous live load deflections, which is delta LL. And we'll be taking a look at the incremental deflections, which are deflections measured after 3 months of beam construction. So when we're looking at incremental deflections, we only consider the creep deflections due to own weight and superimposed dead load. And also the shrinkage is also factored, so we're considering shrinkage deflection after 3 months. But when we're looking at the total deflections, then we have to consider the entire shrinkage deflection and the creep and the instantaneous deflections due to own weight and superimposed dead load. So the different beam types are simply supported beams, two-span beams that have one end continuous, so basically live load being applied on one span, and also three-span beams with both end continuous, so in the analysis that means live load being applied on one span. The variables in the analysis are the steel yield strengths and the quantities, as well as the concrete compressive stresses and the ratios of specified live to dead loads. This figure is showing the variation in effective length to incremental deflection ratios on the vertical axis in two-span beams that have one end continuous, so live load is being applied on one span. On the horizontal axis, we have the span reinforcement ratios. We're comparing in this figure the yield stresses of 400 MPa and 700 MPa, and specified live to dead load ratios are ranging from 0.5 to 1.5. The figure on the right is the associated figure. On the vertical axis, we have incremental deflections, and on the horizontal axis, we have the span reinforcement ratios. The span length is 5 meters, and in 823.3, the ratio limit is 240, and as you can see in the figure on the left-hand side, all the curves are above 240, which means that the deflections are serviceable. And if we're looking at trends, then if we increase the specified live to dead load ratio, K, then we have increased deflections. If we increase the span reinforcement ratio, then we're increasing deflections, and at a higher reinforcement ratio, a higher yield stress gives slightly lower deflections, about 1 to 2 millimeters smaller. In the previous figure, I had used the minimum beam height correction factor, S sub f, which, as I said before, increases as the yield stress increases. And in this figure, it's not being used. And again, on the vertical axis here, we have the span length, effective span length to incremental deflection ratio. On the horizontal axis, we have the span reinforcement ratio. And because the A23.3 ratio limit is 240, we are getting ratios which are 200, which makes the deflections unserviceable. Therefore, we can conclude that S sub f is important to get serviceable deflections. So this figure is showing the refinement of S sub f. On the vertical axis, we have the effective length to incremental deflection ratio. On the horizontal axis, we have the midspan ratio. And the beams are reinforced with yield stresses of 700 MPa and a specified life to dead load ratio of 1.5. And I am varying the concrete compressive stresses between 30 and 90 MPa. And the midspan ratio ranges from 0.006 to rho max, which is the maximum reinforcement ratio possible. And I have basically factored the S sub f, which is the minimum beam height correction factor, so I can reduce the beam height and still satisfy the A23.3 limit, ratio limit. And so at rho max, I am getting 240 as the ratio. And basically, for a concrete compressive strength of 30 MPa, I can reduce S sub f by 19%, and for concrete compressive stress of 90 MPa, I can reduce S sub f by 2%. So in conclusion, the yield stress correction factor for H sub min specified in table 9.2 can't be ignored. And the yield stress correction factor, when it's accounted for, then the beams that meet the H sub min requirement have acceptable incremental deflections, and the incremental deflections increase for higher reinforcement ratios and specified life to dead loads. Okay. So in summary, in chapter 2, we looked at the curvature ductility ratios, which are calculated from moment curvature analyses. And also the best fit equations were calculated from regression analysis. The balance conditions were also checked in beams reinforced with high strength steel. In chapter 4, we looked at the total moment redistribution at ultimate limit states in two span beams, and clause 9.2.4 was verified. And the maximum permissible moment redistribution was also calculated, which basically satisfied the serviceability limit state crack width criteria in ACI 318. And in chapter 4, we calculated the incremental deflections for the various beam types and configurations. And the major conclusions are that A615 grade 100 and A1035 grade 100 have the smallest curvature ductility. From chapter 3, we can conclude that the current provisions in clause 9.2.4, which limit the maximum negative moment redistribution, are conservative for beams with high strength steel. Also, when we are satisfying the serviceability crack width criterion from ACI 318, then there are many factors that should be considered instead of assuming a value of 0.6 Fy. From chapter 4, we can conclude that the high strength reinforcements that meet the minimum beam height correction factor in table 9.2.4 of 823.3 have acceptable incremental deflections when the minimum beam height correction factor is considered. So in the future, I believe we need a more stringent target reliability steel factor in beams for high strength reinforcement. And also we need to review clause 9.2.4 to make the current clause more clear and define C over D, where C is the neutral axis depth and D is the depth of the beam cross section. Also, if the seal area in the cross section is reduced by accounting for moment redistribution at ultimate limit state, then the crack widths should be checked. I would like to thank my advisors for continuously supporting me, and I appreciate the funding from NACRC. Thank you.